Dr. Mamta Bhusry from Department of Computer Science and Engineering, Ajay Kumar Garg Engineering College, Ghaziabad. I will be taking up with you concurrency control in database management systems. The textbooks recommended for this topic are Database Concepts by Koth and Fundamentals of Database Systems by Nawathe. Under concurrency control, we will be discussing three categories of techniques: the locking techniques, timestamp based ordering protocols, and the multi-version techniques. Serial transactions, they result into inadequate resource utilization. This we discussed during my lecture on transaction processing also. This is because of low throughput and low resource utilization in serial transactions and longer response time and more waiting time. To overcome this, the DBMS uses concurrent transactions. We have also seen that concurrent transactions involving the interleaved execution of transactions may sometimes lead to inconsistency of the database. Hence, the concurrency control techniques are required to control the interaction among the transactions in such a way that consistency of the database is maintained. A database may be considered as being made up of a set of data items. A data item may be the complete database, it may be a fragment of the database, it may be a single record, and so on. We have also seen in the previous lectures that concurrent schedules that are serializable produce results which are consistent with some serial schedule of the same set of transactions and are considered correct schedules. Thus, it becomes important that the schedules produced by concurrent transactions are serializable. The concurrency control techniques that we will discuss will try to achieve this. The first technique that we will discuss are the locking techniques. Under this, we will discuss two-phase locking protocols and multiple granularity locking protocols. First, see what are locks and what are the different type of locks. A lock is a variable associated with each data item involved in a transaction. A lock indicates whether a read or a write operation can be performed on the data item or not. Manipulation of the locks leads to either locking the database or the data item and unlocking the data item. Whenever a data item is being accessed by a transaction, then no other transaction must be able to access the same data item in an incompatible mode. This means that a data item can be accessed for reading by any number of transactions at the same time. A data item can be accessed for writing only by one transaction at a specific time, and a data item cannot be accessed for reading and writing at the same time. In order to read or write the data item, a transaction must request a lock on the data item in a particular mode. A transaction can proceed only after the lock is granted to the data item by the lock manager, and the transaction will have to wait if the lock cannot be granted by the lock manager at that time till the lock manager can grant the lock. Two types of locks are defined. First, the exclusive or the write or the update lock, which are generally represented by the symbol X, and the shared or the read lock, generally represented by S. An exclusive lock, it is applied to the data item when the data item is requested for the purpose of writing or updation. When an exclusive lock is applied to the data item, then by a transaction, then only that transaction can write to the data item. No other transaction can access the data item either for reading or writing at that time. A shared lock is granted to the data item when the data item needs to read a shared lock is granted to the data item when a transaction needs to read the data item. Any number of transactions can read the data item at the same time, which means that the shared lock can be applied to any number of transactions at the same time. But a shared lock is not compatible with a write lock. So, any data item that is locked in the shared mode cannot be locked in the exclusive mode at the same time. When the transaction has completed the read or the write operation on the data item, then it releases the lock on the data item using the operation called the unlock, and this is called unlocking of the data item when the data item can be made available to other transactions if possible. The locking protocol, it works as follows, that each transaction before accessing the data item requests the data item to be locked in the appropriate mode, that is the shared mode or the exclusive mode, depending whether the transaction needs to read or update the data item. The following cases may arise. First, the data item is not already locked when there is a request for locking, then the requested lock is granted. The second case can be when the data item is already locked in the shared mode, then under such circumstances the lock request in the shared mode can be granted, but lock request in the exclusive mode cannot be granted. The third case is if the data item is already locked in the exclusive mode, then a lock in the shared mode or the exclusive mode cannot be granted. The following is the compatibility matrix for the locks, and here we see that a shared mode lock is compatible with a shared mode lock, meaning that at any point of time if a data item is locked in the shared mode, then it can also be locked in the shared mode by another transaction. The shared mode lock is not compatible with the exclusive mode, that is, if a data item is already locked in the shared mode by a transaction, then it cannot be locked in the exclusive mode by another transaction. The exclusive lock is not compatible with the shared lock. So, a data item being locked in the exclusive mode cannot be locked in the shared mode. Exclusive mode is not compatible with the exclusive mode, which means that the data item being locked in the exclusive mode cannot be locked by another transaction in the exclusive mode. We will generally use the following notations for locking and unlocking of the data items. Here lock XQ means that a lock, it means that the exclusive lock is requested on the data item Q. Lock SQ means that the shared lock is requested on the data item Q, and unlock Q means that the data item Q is being unlocked. Just applying the locks and releasing them may not be sufficient to achieve serializable schedules. What is important is the positioning of the locks, and this is used and this is achieved through the locking protocols. A locking protocol is a set of rules followed by the transactions while requesting and releasing the locks. Now, let us consider this schedule of the transactions T1 and T2 and let the initial values of x and y, which are the data items here, be 20 and 30 respectively. So, as the transaction T1 proceeds, we see there is a shared lock on the data item y, there is a read of y, unlock of y, that is data item y is released, lock, exclusive lock on x, x is read, x is x plus y, which gives the value of x as 50, 20 plus 30, unlock x. Then we have a shared lock on x, read of x 50, that is the value that was written here, unlock x, lock x in exclusive mode, sorry, lock y in exclusive mode, read it, the value of y is modified to 80 and y is written. So, we get the final values of x and y as 50 and 30. Now, let us look at this. This is a concurrent schedule with the same set of transactions T1 and T2. In this case, we get the values of x, the final values of x and y as 50 each. This is another schedule of the transactions T1 and T2, and this is a serial schedule where we are getting the final values of x and y as 70 and 50 respectively. So, from these three schedules, we see that this concurrent schedule does not give the final values of x and y the same as any of the two possible serial schedules. Now, why has this happened? This has happened because the unlock of y was performed very early in this case. So, when y was unlocked, it could be locked here with the it could be locked here in the exclusive mode by the transaction T2. So, had this not been unlocked over here, we could have achieved the correct state of the databases. That is why we said that the positioning of the locks is very important. So, we will study the two-phase locking protocol to see how the positioning of the locks should take place. This protocol guarantees conflict serializable schedules, which we have already studied earlier through the monotonic locking and unlocking of the data items. All the locks are first acquired before any of the locks can be released in a transaction, and after any of the lock has been released in a transaction, no additional lock can be requested by the transaction. Or we can say that the release of locks is delayed until all the locks they are required by the till all the locks are acquired by the transaction. So, we can define the two-phase locking protocol as consisting of two phases, phase 1 which is called the growing phase or the expanding phase, and the phase 2 which is called the shrinking phase or the contracting phase. During the growing phase, the transaction can only obtain the locks, it cannot release any lock. Whereas, during the shrinking phase, the transaction can only release the locks, it cannot obtain any lock. Consider these two transactions. In this transaction, we say that there is a exclusive lock requested, there is a exclusive lock on A here, unlock B, unlock A. So, first all the locks are being acquired and then the locks are being released. So, this transaction is said to be in two-phase locking. Whereas, consider this transaction, here we have a lock, here we have a lock x, then x on B, then we have unlock B, again we have a request for a lock on A and unlock A. That is, it is not following the two-phase locking protocol, where we need to first acquire all the locks and then release all the locks. So, we say that this transaction is not in two-phase. The two-phase locking protocol, it does not ensure freedom from deadlock and cascading rollback. Let us see how. We already know the definitions of cascading rollback and deadlock. Cascading rollback occurs when a single transaction failure leads to the series of transaction rollbacks, whereas a deadlock, it occurs when all the transactions involved in a schedule, they are waiting for some other transaction to release a data item so that they can proceed. So, what results into it is a deadlock when none of the transactions can proceed. So, we will just go through this example to see how a locking protocol can lead to a deadlock. We have a X lock request over here. So, read B, write B. T3 performs the read B and the write B. Then we see a shared lock is requested on A, it performs the reading of A, and after that there is a shared lock on, after that there is a shared lock request on B. But since B is already held in the exclusive mode by T3, so the shared lock over here cannot be granted and T4 has to wait for the data item B to be released by the transaction T3. In the meantime, there is a exclusive lock request by T3 on A. A already being locked in the shared mode by the transaction T4, the lock to T3 cannot be granted and it has to wait for the lock to be released by T4. So, both T3 and T4, they are waiting for each other to release the data item, and hence they are said to be deadlocked because neither of them can proceed. Now, let us see in this example how a two-phase locking protocol can lead to a cascading rollback. We have the transactions T5, T6 and T7. T5 locks A in the exclusive mode and unlocks A over here. T6 locks A in the exclusive mode, unlocks here, and T7 locks it in the shared mode and reads the value. Now, all these three transactions T5, T6 and T7, they are in the two-phase locking. But if the failure of T5 happens after read A of T7, that is after T7 has read the value of A, if T5 fails, then let us see what happens. Because the value of A written by T5 has already been read by T6 and updated, it has already been read by T7. So, if T5 fails, it is required that both T6 and T7 be rolled back because they have already read the value of A which was updated by T5. Thus, a cascading rollback takes place. Now, cascading rollback, it can be avoided using the variations of the two-phase locking protocol called the strict two-phase locking protocol and the rigorous two-phase locking protocol. A strict two-phase locking protocol is that where the transaction must hold all the exclusive locks till the transaction commits, whereas and hence no other transaction it can read or write the data item that is written by T unless T commits, because it is holding the exclusive lock on the data item till its commit. A rigorous two-phase locking protocol, it is a more strict version of the strict 2PL, and under this a transaction T, it must hold all the locks that is shared as well as exclusive on the data items it is using till it commits or aborts. Both the strict two-phase locking protocol and the rigorous two-phase locking protocol ensure freedom from cascading rollback, but they still cannot avoid deadlock. So, we have already seen that one problem with the 2PL protocol is the deadlock. Another problem that takes place with the two-phase locking protocol is the problem of starvation. Let us look at this example where we see that we have transactions T1, T2, T3 and T4 which are using the data item Q. Here transaction T2 has locked the data item Q in the shared mode. Transaction T1 is requesting a lock on the data item Q in the exclusive mode. In the meantime, T3 is also requesting a shared lock on Q. T2 unlocks the data item Q. So, that means it is available, but T3 has already requested a shared lock on it. So, it has got the shared lock on the data item 3. Here T2 was holding a shared lock. So, when T3 requested the shared lock, it got the shared lock, because shared lock is compatible with a shared lock. So, on unlocking of the data item Q by S, T1 is still not able to get an exclusive lock on the data item Q. Next, T4, it requests a shared lock on the data item Q, which it gets because T3 is holding the data item under a shared lock. T3 unlocks the data item Q, but at this point T4 is still holding the data item Q in the shared lock, and hence the transaction T1 still cannot get the data item Q. So, whereas other transactions T2, T3 and T4, they are able to get access to the data item, the transaction T1 is not able to get access to it. This phenomenon is called starvation, and locking protocols can sometimes lead to starvation when a data item is made to wait very long for the lock that it has requested. After the two-phase locking protocol, we will study what lock conversions are. Sometimes it may be desirable to permit lock conversions. A lock conversion means converting one type of lock on the data item to another lock. So, a lock conversion may allow a shared lock to be converted to an exclusive lock, or an exclusive lock to be converted to a shared lock. Let us see why we may need lock conversions. In this example, we see that T8 has locked the data item A1 in the exclusive mode. In the meantime, the transaction T9 is also requesting A1 in the shared mode, but since it is already locked in the exclusive mode by T8, it cannot get access to it. Through T8, we see that TA, though it is holding a exclusive lock on TA, but it requires to write to A1 only at this time, whereas T9 had requested the shared lock over here. So, had it been possible that T8 acquires a shared lock on the data item A1 here, so that T9 can also get a shared lock on the data item A, and when T8 needs to write to the data item A1, it can simply convert the lock to a exclusive lock. So, the transaction T9 will not be made to wait for the data item A1 for reading. This is why we can say the conversion of the locks is required. So, we say that this observation leads to the refinement of the two-phase locking protocol with the lock conversions. Two types of lock conversions are possible, the upgrade and the downgrade. A shared lock can be upgraded to a exclusive lock, and this means that this can take place only in the growing phase of the two-phase locking protocol. An exclusive lock can be downgraded to a shared lock, and this can take place only in the shrinking mode of the two-phase locking protocol. So, we will see a lock conversion example over here. Here T1 is locking A1 in the shared mode and A2 in the shared mode. T2 has requested shared mode lock on A1 and A2, and it gets the lock because the transaction T1 is holding the data items in a compatible mode. T2 unlocks A1 and A2, and then T1 upgrades the lock on A1 to an exclusive lock. When we write upgrade A1, it simply means that the lock has been upgraded. Upgraded means conversion from shared lock to exclusive lock. The two-phase locking protocol with lock conversion, it is defined as follows. During the growing phase, the following can happen. The lock in the shared mode can be acquired, locks in the exclusive mode can be acquired, and the lock can be converted from the shared mode to the exclusive mode. During the shrinking phase, the shared mode lock can be released, the exclusive mode lock can be released, and a lock can be downgraded from the exclusive mode to the shared mode. And just like the basic two-phase locking protocol, the locking protocol with lock conversion generates conflict serializable schedules. Our next locking technique that we will study is the multiple granularity technique. We have already seen earlier that a database can be chosen to be, a data item can be chosen to be any one of the following. It can be a database record, a field value of the database record, a disk block, a whole file, or the entire database. So, based on what we are considering as the data item, we generally say that we have two types of granularities, the fine granularity and the coarse granularity. The fine granularity, it refers to small size of the data items, that is, if we say the small size of the data items, we may say a database record, whereas a coarse granularity, it refers to the larger size of the data item, let us say the database as a whole. Larger the data item size, the lower is the degree of the concurrency achieved. Why? Because if let us say we are considering the data item as the entire database. So, only one transaction may be able to lock the data item for writing. So, the coarser the granularity, the lesser is the degree of concurrency. If we have fine granularity, that is, let us say at the record level, then the different transactions may be able to access the different records, and hence there is a higher degree of concurrency. Here we have shown a multiple granularity hierarchy with the database at the top, the coarse granularity, and the records at the lowermost levels, which is the fine granularity. The next question that comes is that what is the best granularity? As such, there is no best granularity. It really depends upon the type of the transaction. If a transaction accesses the small number of records, then it may be advantageous to have the data item granularity to be, it may be advantageous to have the data granularity to be small or fine, whereas if the transaction needs to access the large number of the records from the same file or the block, then we may prefer a coarse granularity. Now, when a transaction locks the data item in the hierarchy explicitly, it will implicitly lock all the descendants of that node in the hierarchy. So, if a transaction is locking a data item or a node in the shared mode, then the node in question is locked explicitly in the shared mode, and all the descendant nodes to it are locked implicitly in the shared node. Lock nodes, whether it is explicitly or implicitly, they are available only for reading. When a node or a data item is locked explicitly in the exclusive mode, then the node in question is locked in the exclusive mode, and all the descendant nodes, they are locked implicitly in the exclusive mode. No transaction can concurrently access these data items which are locked explicitly or implicitly in the exclusive mode. In order to make the multiple granularity technique even more effective, additional locks which are called the intention locks, they are needed. We have three types of intention locks: intention shared lock, intention exclusive lock, and the shared intention exclusive lock. Let us see what these are. An intention shared lock indicates that the shared lock will be requested in some of the descendant nodes of the current node. An intention exclusive lock means that some exclusive lock will be requested on some descendant nodes of the current node, and the shared intention exclusive lock means that the current node is locked in the shared mode, but exclusive locks will be requested in some descendant nodes. This is the compatibility matrix for the intention locks. We see that the intention shared lock is compatible with the intention shared lock. It is compatible with the intention exclusive lock. It is compatible with the shared lock and with the shared intention exclusive lock. Intention exclusive lock is compatible with intention shared, intention exclusive, but is not compatible with the shared and the shared intention exclusive lock. And similarly for the shared lock, the shared intention exclusive lock and the exclusive lock. We will use this compatibility matrix in solving some questions. Before that, let us see how the multiple granularity locking protocol works. The locking compatibility matrix that we have just seen implies that the conflicting locks cannot be granted. The root of the hierarchy must be locked first in any mode. A transaction T can lock a node only if it has not unlocked any of its descendant nodes, which is in accordance with the 2PL. Only if it has not unlocked any node which is in accordance with the 2PL protocol, and a transaction T can unlock a node N only if none of the children nodes of N are currently locked by T. So, these rules, they ensure the serializability of the schedules. The multiple granularity locking protocol requires that the locks be first applied in the top down fashion, that is, should be applied from the root to the leaf and should be released from the leaf to the root of the hierarchy. Now, let us consider this example. We have this multiple granularity hierarchy over here, and we say for the given database hierarchy, show that the multiple granularity locking scheme to lock the record R13. So, which is the record R13? R13 is over here. We have to lock the record R13. Just a moment. So, R13 is here. How will the multiple granularity locking protocol work? First, the database, it will be locked, because this has to be locked in the for retrieval only, that is in the shared mode. So, that means the database will be locked in the intention shared mode lock. The partition 1 will be logged in IS lock, the record type 1 will be logged in IS mode, and R13 will be logged in the shared mode. Let us take up another example. Which says, For the same database hierarchy, show the multiple granularity locking scheme to lock R22. Let us say R22, okay. R22 is here in the exclusive mode. So, how does the locking scheme works? Database in IX mode, partition 1 in IX mode, record type 2 in IX mode and R22 in X mode. So, this is how the locking scheme will work. Let us consider this example. For this given hierarchy, illustrate the multiple granularity locking scheme for the given database hierarchy and transactions. T18 wants to read the record RA2. So, that means what does T18 do? T18 locks this in the IS mode, locks this in the IS mode, T18 locks FA1 in the IS mode and it locks this in the shared mode. Next, T19 wants to modify the record RA9. Let us consider this as RA9. Let us consider this as RA9. So, what happens? T19 will lock this in the intention exclusive, T19 will lock this in the intention exclusive, and this in the exclusive mode. Next is transaction T20 wants to read all the records in the file FA1. So, what T20 does is IS, T20, IS and T20 wants to read all the records here. So, it is shared mode. T20 wants to read the entire database. So, what T21 does is it applies a shared lock over here, right. So, basically I will just show you what we get. At the end of it, we get this. So, from here we can see that since IS and IX locks, they are compatible, but IX lock is not compatible with the shared lock, right. So, over here these two cannot take place. Over here T18, IS, IX and IS, they are all compatible. Here these two, they are not compatible. From this we can conclude that in this example T18, 20 and 21 can access the database concurrently. How? T18, T20 and 21, this and this can access the database concurrently, but T19 can execute concurrently with 18, but not with 20 or 21. So, T19 cannot execute concurrently with, from here we know, with 21, and it cannot execute concurrently with T20. Yeah. So, these are the conclusions that we have if we try to imply the multiple granularity protocol to our hierarchy that was given. The multiple granularity protocol is especially suited when processing a mix of transactions which include short transactions that include only a few items and the long transactions that access the entire file or the pages. Thank you.